Okay, hi everyone. I think because maybe we probably won't have enough time to go through all these extra classes before your trial exam. So I thought I'll record this and I will answer all the questions in this handout so that you can do the revision based on this lah. Okay. All right, so we're going to the first question. Diagram 1 shows a spring balance. Okay, and then of course in spring balance, it can be something to do with weight. It can be something to do with Hooke's law, depending on what the question is. The physical quantity measured by the spring balance is, of course, it is weight lah. Okay, because this is the standard one for spring balance, especially if the spring balance unit is given in newtons. Okay, what is the value of the accuracy of this one? Actually, if you look at it, sorry, I have to zoom in a lot closer. Okay, so accuracy, when we're talking about the words accuracy, we're looking at this thing. What is the value of the smallest line? Okay, so if we take a look at this, it's 0 and then 1, and then in between there's one line, right? So since there's only one line, it'll be 0.5. Okay, so and we're going to assume that it's newtons lah. You know why? Because it's given in the question. Sorry, not assume lah. We have to, memang it's newtons. Okay, so the accuracy of the spring balance is 0.5 newtons. Okay, and then the reading shown by the rod. Okay, if we zoom in, the reading is actually about 2.5. Okay, so we will have 2.5 newtons over here. So state one characteristic of the spring used in the tool. Usually characteristics of the spring is, of course, it has to be elastic lah, because the most important thing is that it must come back to its original position. Okay, after you take out the weight, okay, dia tidak boleh kendur lah, it has to go back to its original position. So one very important characteristic will be the elasticity. Okay, number 2, you're shown a velocity time graph. Okay, just to recap, if a velocity time graph, the gradient represents the acceleration. Okay, and the area under the graph, okay, represents the distance traveled lah. Okay, or the displacement lah. I guess at our current level, both ways also can lah. Okay, so these are things to remember when you approach the graph, but not necessarily they will ask lah, but it's good to know. Okay, so the first question is the velocity can be defined. Okay, velocity is of course the rate of change of displacement, because rate of change of distance is speed. Okay, because distance is a scalar quantity, velocity is a vector quantity. Okay, vector quantity, All right, so state the type of motion of the bus after 10 seconds. So that means we are talking about this section after 10 seconds. So we notice that the velocity is decreasing. Okay, so you can say decreasing velocity, okay, or constant deceleration. Now it's constant deceleration. This one is usually comes as a pair. Okay, so remember the pairs there are. Usually if it is increasing velocity, okay, it will be a constant acceleration. Another one is constant velocity will be zero acceleration. These are all pairs that come together. Okay, so we need to remember this as pairs. Okay, determine the position where the bus is accelerating. Okay, I guess the question is a little bit strange, but we obviously know that acceleration happens when velocity is increasing. So this section is where the velocity is increasing. I would say from X to Y. Okay, I know it says position. It's a bit funny. It shouldn't say the word position, but I can't really think of a better word for this. But it should not be saying position. Okay, but we say X to Y. Okay, name the physical quantity represented by the area of the graph. As I said just now, the area of the graph represents the distance traveled. This is actually my favorite. Okay, my favorite answer is this, distance traveled. Or you can also say the displacement if you want, since it is all moving to the right. Okay, if you know this graph very well, everything on the top is moving to one direction. So you can say displacement. But if let's say your graph, it goes up and down like this, right? I would not recommend you to answer displacement because it's going to the right and then it's going to the left. So if you say displacement, yes, the area of the graph will actually, I would not recommend, but it would still be correct, I guess, if you take into consideration the positive and negative. Okay, but it's a bit dangerous. But in any case, okay, if you don't want to get into the technicalities of it, you can still give both answers. I think it's fine. Okay, all right. Next question. Diagram 1 shows an experiment to study the phenomenon of sound waves. So sound is obviously a longitudinal wave. Okay, sound is the only wave that is longitudinal wave. Everything else is transverse wave. Okay, water waves, light wave is electromagnetic. Okay, but most of the other things are transverse wave. Only sound we know is longitudinal. Okay, now the wave phenomena that is involved, okay, this one is obviously reflection. Okay, now in your syllabus, there are 6 wave phenomena that you need to remember. Okay, of course, the first one is damping. Damping is where the wave becomes less and less stronger. The second one is resonance. Okay, this is also considered a wave phenomena. And then, of course, we have the big 4. Okay, we have reflection, refraction, diffraction, or some people like to pronounce it as diffraction, and then lastly is interference. These are the big 4 okay, that is the most commonly asked: reflection, refraction, or diffraction, and interference. Okay, so once you are used to these kind of words, I mean, the question cannot run away very far. It is called a wave phenomena. So if you know, oh, okay, these are the wave phenomena, so you choose one that is suitable with this current picture. Okay, state the angle of reflection if the angle of incidence is 30 degrees. Obviously, it's 30 degrees because angle of incidence is equals to angle of reflection. Okay, state the change in the velocity of the sound wave heard by the observer. Okay, now technically, okay, technically the speed doesn't change. Okay, after reflection, okay, after reflection, if the wave is going here at, say, for example, 600 meters per second, it's also going to flow back here at 600 meters per second. But the question is worded very funnily. Okay, the question asks for velocity. Okay, so I would say it will be, I would say same magnitude, but different direction. Okay, this is a very, very strange question because usually when we talk about wave, we don't really talk about the wave velocity. We talk about the wave speed. Okay, so the wave speed will be the same. If you go 600, you come back 600. But now the question is asking for velocity. So I feel that this may be a technical question, or it could be that the person who did this question forgot that velocity is a vector quantity, so you have to take into consideration the direction. But since the question is asking velocity, I'm going to give the answer in terms of velocity. Okay, now in reflection, remember, speed doesn't change. Okay, the speed remains unchanged. But since this question is asking velocity, we say it is the same magnitude, nilainya sama, okay, cuma arahnya berlainan. The direction is different. Okay, all right, next. Diagram 1.1 shows a spoon that appears bent. Okay, so this, of course, this light phenomenon is called refraction. Anything to do with bending, okay, the bending of waves, the changing of direction of waves usually is refraction. Okay, so obviously we're talking about this refraction of light. Okay, all right, then name a physical quantity that changes when light propagates from water to air. Okay, so there are 2 things that change, which is the wave speed or the wave length. Okay, just as a reminder, the one that is unchanged, okay, for refraction, the one that is unchanged is frequency. Okay, So we want to kind of remember that lah. Frequency is never changed, okay, during refraction. Okay, next, complete the ray diagram, etc., to show the reflection of light that occurs on the spoon. Okay, so when you draw this, the most important thing is the image must have a straight line to the eye. Okay, so the image must have a straight line to the eye, so you will have to draw a dotted line like this. Sorry, something like that lah. Okay, a dotted line that looks something like this. Okay, but the other one is, where does the straight line come from? It comes from the refraction of light, because the original one is here. Okay, the original light is this one that goes and then reflects into this one, but our eyes see it as a straight line. That's why it looks shorter than it actually is. Okay, sorry, let me rub this off because this is not part of the answer. Okay, this is the answer. This one is the answer. Okay, so it's 2 marks. 1 mark for uh 1 mark for the straight line over here, and another mark for the dotted line. Okay, usually we will write it as a dotted line lah. Okay, so that it will show that that's not the light that's traveling. The light that's traveling is the one with the straight line. Okay, let's continue to the next question. So diagram 1 shows a consumer needs to undergo a body temperature check. So temperature is the degree of hotness. Okay, obviously lah, because the form of energy is heat. So just remember, temperature, the definition is the degree of hotness. Heat is a form of energy. All right, state the type of physical quantity measured by the thermometer. Of course, it's temperature lah. Oh, sorry, this is type. Sorry. Type, that means temperature is either a scalar quantity, okay, or it's a basic quantity. Okay, or otherwise known as a base quantity lah. I think these two words are similar and can be accepted. Okay, state the unit represented in diagram 1. So diagram 1, since this is 36.6, obviously this is degrees Celsius lah. Okay, just as a reminder, if you write degrees Celsius, you need to write the small degree sign lah, not just this one. So what is the reading of diagram 1 in SI unit? So 36.6 degrees Celsius is not SI unit. SI unit for temperature is Kelvin. So it will be 36.6 plus 273. Okay, 309.6. Okay, 309.6. Of course, you have to state the Kelvin lah. Okay, because this is SI unit. All right. Okay, let's move on to question 2. Okay, diagram 5.2 shows, sorry, 2.1 shows the start and end positions for Adam while cycling. So Adam goes to the right, U-turns, and then continues on to the left. Okay, so the displacement time graph is shown here. So what is the meaning of displacement? Okay, shortest distance from the starting position. Okay, they're from the starting position or from the original position. There are quite a number of definitions for displacement. Okay, what happens? Okay, what happens to Adam's motion from the 10 to 12 moment? Okay, so 10 to 12 moments, since there is no change in displacement, so actually Adam is stationary. Okay, now calculate the total distance of Adam. Even if you don't really follow this, you can actually look at this. So he starts here, 70 here, and then 70 back is 140. Okay, the distance, and then tambah another 40, those used to be 180 lah. Okay, 180 meters. Now calculate the average speed of Adam. So average speed is distance over time. Okay, so the distance is 180 and the time is 20 seconds. Okay, so this will be 9 meters per second. Okay, so I guess 2 marks over here will be 1 mark for the calculation and 1 mark for the answer with the unit. Now, don't forget that even if the question is like dot 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 dot, there's no space for you to do calculation, doesn't mean that you don't have to show your calculation. You still need to. Okay, because take into consideration the number of marks given. Okay, this is an answering technique lah. Okay, shows a large pot with noodles being cooked in a large amount of hot water. So what is the meaning of heat? We just covered this is a form of energy. This is a very funny definition if you think of it. Heat is about energy, but how the rest are electricity sound also forms of energy, right? I guess they ran out of words for this one. Now, why is the noodle being cooked in a large amount of hot water? So a large amount of hot water usually refers to a big mass lah. Okay, and a big mass of water or hot water means that it has a big amount of heat. Okay, yeah, big heat capacity lah. Okay, so that it can transfer the amount of heat, the heat to the noodle. Okay, so of course this is a 2-mark question. Okay, so the first one is you need to state that the mass of the hot water is large. Okay, mass of hot water is large so that, okay, so this is 1 mark. Okay, the mass of the hot water is large so that, okay, it has a large heat capacity. Okay, so this would be another mark. Okay, or if you say the mass of the hot water is large so that it can transfer, okay, so I'm giving an alternative answer lah. Okay, so that it can transfer a lot of heat to the noodle. A lot of heat or more heat to the noodle. So this is also an acceptable alternative answer. Okay, but of course, when you talk about large amount of water, that one needs to be mentioned. The mass of the hot water is large. Okay, 2 kilograms of water at 30 degrees Celsius is being added to 9 kilograms of water at 95 degrees Celsius. Okay, so what is the final temperature of the mixture lah? Okay, let's take the low one first. So the low one obviously is going to increase in temperature. Okay, so obviously we're using this one M1, C1, theta 1. Okay, but the good news is the C is the same because the both is water. Okay, equals to M2, C2, theta 2. So the C is the same. Okay, since the C is the same, they can cancel each other out. Okay, so you will have M1 is 2. Now, since theta 1 is an increase, it's going to increase from whatever final temperature to whatever final temperature from 30. So it will be theta minus 30, the final temperature lah. Manakala, this 9 kg is going to decrease. So decrease means 95 minus theta. Okay, so this will be 1 mark. And then when you finally calculate, you get theta is about 83.18 degrees Celsius. Okay, when answering a thermal equilibrium question, the most important thing to remember is the one that is going up is always theta minus the original. Okay, and the one that's going down is the original temperature minus theta. Okay, the final, this one lah. Okay, so we have a penyembur racun serangga, which is you know, the spray thing. So whenever we're talking about the insecticide sprayer, the principle that's usually involved is Bernoulli's principle. Okay, and Bernoulli's principle is the one which says small velocity, high pressure, or high or low pressure, high velocity. Okay, so either way lah. Now, one thing to take note is don't get the spelling of Bernoulli wrong. Okay, that's a very important thing to take note of. Oh, sorry. Okay, so based on diagram 2, take the correct answer in the box provided. Which region experiences low pressure? Okay, so let's think about this. When you push this one in, okay, when you push this one in, the speed of the wind is going to be high. Okay, the speed of the wind coming up, because the nozzle is so tiny, right? The speed of the wind here is going to be high. So obviously the pressure will be the lowest here. So it will be this. So what makes the water come out? What makes the cecair come out is, since the pressure over here is low. Oh, sorry. Astaga. Okay. Since the pressure over here is low. Okay, since the pressure over here is low because of the high velocity wind. Okay, the atmospheric pressure is going to push the liquid up. Okay, whenever you think about atmospheric pressure, we need to remember that actually a lot of things we do, the atmospheric pressure is the one that is doing most of the work. Okay, for example, when we're drinking water from the straw, right, all we're doing when we're sucking is just we're sucking all the air out. And that's all we're able to do. Technically, we're not really pulling the water into our mouth. It is the atmospheric pressure that is pushing the water into our mouth. Okay, so don't perasan diri and say it's so strong that you can suck the water into your mouth. No, the one that is really doing the work is actually the atmospheric pressure. Okay, give one reason for your answer in B. So they say, okay, the velocity or the speed, okay, of the air is high at Y. Okay, so explain how the insecticide sprayer produces a fine spray liquid. So it will have something to do with the atmospheric pressure pushing the liquid up the narrow tube lah. Okay, so that's number one. So you need to write that when the region Y is at low pressure, okay, due to the fact that the velocity of the air is high, okay, the atmospheric pressure pushes the liquid up the narrow tube. Okay, that will be the first mark lah. Okay, this one will push the thing up the narrow tube. And then of course, the narrow tube over here, okay, in this one will the liquid, okay, will be carried out. It's a very strange word lah, carried out, but yeah, let's just use it anyway. Okay, from the narrow tube in tiny droplets. Okay, which explains how it can produce the fine spray liquid. So each one of these will be 1 mark each. All right, let's go to the next set of questions. Question number 3. So what is the meaning of impulsive force? So impulsive force is the rate of change of momentum. Okay, for definition, can't really run much from there. Okay, explain how the crumple zone reduces the impact. So whenever you're talking about impulsive force, okay, there are always two things that you need to think about lah. Okay, which is the time of collision, okay, masa pelanggaran, yeah, the time of collision, and then of course the big impulsive force lah. So the crumple zone, okay, crumple zone increases the time of impact, 1 mark. Okay, and then as a result, okay, to reduce the impulsive, sorry, yes, my dog. Okay, to reduce the impulsive force. This always comes as a set one. Okay, increase the time of impact, reduce impulsive force, or the other way around. Okay, and we find out that usually impulsive force questions, they will always tend to ask these 2 mark explanation questions, okay, to elicit this answer from you lah. So remember this as a set, okay, as a set of questions lah. All right, if the car in diagram 3 stops in 15 seconds, calculate the impulsive force acting on the car. Okay, so the impulsive force, the formula for impulsive force is F equals to mv minus mu over t. Now the time, of course, is given in 15 seconds. Our mass is 1,500, 100 kilometers per hour to 0. Okay, so it'd be 1,500. It'd be 0 minus 1,500. I'm just going to use, sorry, I can't use because it's in seconds. So I will have to change the 100 kilometers per hour, okay, to meters per second. Okay, and how do we do that is we change the kilometer to meter first by times 1,000. Okay, kilometer to meter is times 1,000. Okay, then you divide by, okay, hour to second, by hour to second is times 60 times 60 lah. Okay, because 1 hour is 60 minutes and 1 minute is 60 seconds. So 60 times 60. Okay, and so you will get just about 27.78 meters per second. Okay, meters per second lah. Okay, uh if you really are lazy to remember this, I mean, you can actually simplify this lah. Okay, this will be 100 times 5 over 18. Okay, this seems to be the magic formula to change from kilometer per hour to meters per second. Okay, so anyway, once you calculate this, so obviously this is 1 mark lah. Okay, the changing of kilometer per hour, 100 kilometers per hour to meters per second, okay, is the first mark. The second mark is the substitution. And of course, the third mark will be negative 500 times 27.78 divided by 15. Okay, will give you about 2778. Okay, newtons. And that's what we want lah. 1500 times 27.78 divided by 50. Yeah, 2778. Okay, 2778 newtons, which is quite a big impact lah. Okay, because the time of collision is, although it's 15 seconds, yes, it's very long. But imagine if it's even shorter. Okay, so but of course, because this one is we're talking about cars, so obviously the impact is much bigger lah. Okay, let's continue. Right. So diagram 3 shows a man pulling a sack containing a fruit of mass 7 kg upwards with a pulley of a force 68.67 newtons. So here is 68.67 newtons. There's of course the mass and the gravity over here. Okay. And then there will be a tension on the string over here lah. Okay, so what is meant by forces in equilibrium? It's when the resultant forces acting on an object is 0. Okay, that's when all all the forces will be in equilibrium. Okay, so second question, based on the diagram 3, sketch the free body diagram to show the two forces that are acting on the block. So obviously we're talking about these two. Okay, so let's put the sack over here, and then this will be the tension of the string, and then this will be the weight. Okay, I think I think that will be enough as long as there's just two lah. Okay, the tension of the spring and the string. Okay, and the weight. All right. What is the value of the downward acting force? Obviously, it will be the same value as the upward lah. The value only. So if it is 68.67, it will be 68.67 newtons. Okay. So the question is, what is the force that must be applied by the man, okay, to move up with the sack with an acceleration of 2 meters per second? Okay, so we're having the force, okay, which is by the string lah. Okay, so you want to know how much to increase this force, okay, in order for you to accelerate it as 2. Okay, so since when it is in equilibrium, it is 68.67. So we know that the weight is 68.67. Okay, so the force that you're pulling it with minus the 68.67 must be equals to the 7 kilograms, okay, times the acceleration, which is 2, because we're using the net force equals to mass times acceleration. Okay, so after that, when you calculate this, then you will get about 82.67 newtons. Okay, F lah. So in order for him to overcome the 68.67 Newton weight, okay, he has to pull with a force of 82.67 newtons. Okay, then he can get an acceleration of 2 meters per second. Okay, the next question, diagram 3 shows a weather forecast satellite orbiting at a certain altitude around the Earth with an orbital radius r and a linear velocity v. Okay, so state one factor that affects the linear speed of satellites circulating on the surface of the Earth. So the formula for linear speed, okay, is v equals to gm over r square root. Okay, and since this is the Earth that we're talking about, so the mass of the Earth doesn't change. So actually only the distance from the Earth, okay, is the factor lah. So the distance from the surface. Oh no, not the surface, the distance from the Earth. Let's just, distance from the Earth. Okay. because the mass is the same, mass of Earth, so you can't really put that as a factor, okay, unless you're talking about different planets. Okay, so the satellite has a mass of 419,725 kg, okay, and has an orbit with an altitude of 600 kilometers from the Earth's surface. Okay, the linear speed of the satellite is what you want to calculate. So this is V equals to Gm over R square root. Okay, and then this is where obviously you will have to have all this one. So G is 6.67 times 10 negative 11. Okay, the mass of the Earth, I don't think they give it here, but they will probably give it much this one. Okay, the mass of the Earth is actually, hold on, 6 times 10 to the power of 24. Okay, okay, the distance is 600 kilometers from the Earth's surface, but, okay, we are talking about the distance from the center of the Earth. So the radius of the Earth is 6.37 times 10 to the power 6 plus 600 kilometers. 600 times 10 to the power 3, because you need to change this into into this one. So notice that actually they're not giving you the mass of the satellite has no play in the linear speed. Okay, the mass of the satellite is just like, oh wow. Okay, so 6.67 times 10 negative 11 times 6 to the power of 24, 6 times 10 to the power of 24, divided by 6.37 to the power of 6 plus 600 to the power of 3. Okay, so when you've calculated the linear speed of the satellite, it's about 7.577 times 10 to the power of 3 meters per second. Okay, so then after that, you calculate the centripetal acceleration, which is A equals to V squared over R. Okay, so you get the V 7.577 times 10 to the power 3. You square it over the same R that we used over here. Okay, so 6.37 times 10 to the power 6 plus 600 times 10 to the power 3. Okay, and so when you calculate this, okay, you get about 8.24 meters per second squared. Okay, which sounds just about right lah. Okay, notice that the question is giving you the mass of the satellite, which actually has no point here, because when you talk about linear speed, it depends on the mass of the Earth. You talk about centripetal acceleration, it depends on the linear speed. So the mass of the satellite is actually a dummy. Okay, so we have to be very clear. The mass of the Earth is for which formula, the mass of the satellite is for which formula. We cannot mix these two up. Okay, so give an example of Malaysian-made satellite. Obviously, it's Miasat lah. Miasat 1 or Miasat 2 is a very obvious one lah. Okay, simple hydraulic system over here is 20 newtons. So whenever you see hydraulic system, obviously it will be Pascal's principle. Okay, so the pressure acting on the oil. So you have the small one is 0.1, the big one is 0.5, and then the small one is 20 lah. So this will be F1 over A1 equals to F2 over A2. Okay, you want to calculate the pressure that is acting on the big one, okay, which is at the oil. Okay, so F1 is 20 over 0.1 equals to F2, which you want to find, over 0.5. So when you calculate this, you will get about 100 newtons. Okay, 1 mark for the substitution, 1 mark for the answer. So, oh, sorry. Sorry, this is the answer for this one. The pressure acting on the oil is just this one. Okay, 20 over 0.1. So 20 divided by 0.1 is about 200 pascals. Okay, sorry, I've misread the question. Calculate the pressure. So the output force is the 200 equals to F2 over 0.5, because Pascal's principle is pressure at the small one is equals to the pressure at the big one. Force is different, but pressure is the same. So what will happen to the output force if the diameter of the output cylinder is larger? So obviously it will increase lah. Okay, because according to pressure equals to force over the surface area. If I bring this up, if the pressure is constant, the area is actually directly proportional to the force. So the bigger the surface area, you will get a bigger output force lah. Okay,
So that's it for the first video, question 1 to 3. I'm going to answer it in different videos so that you can take your time to see which one you want lah. So in the next video, I will cover questions number 4, 5, and 6. All right, take care, everyone.